Good morning. I would like to thank the organizer for this kind of invitation. I was a student here many, many years ago, so it's always a great pleasure to be here. I'll talk about new 2D materials from non-vulnerable solids, but before I'll give you an overview of the simulation tools you can use for 2D materials. So I'd like to thank the collaborator. We have many experimental groups in this works, and also the funding agency that's in Brazil now. It's become more and more important. Okay. With the advent of graphene, it started a real revolution in material science. But graphene has not only very unique electronic property, it has also very unique mechanical property. It's the ultimate membrane, just one thick atom. You cannot go below that. But also, the fractal in graphene is unique. Instead of having just the fractal with the general shape of the ballistic projectile, graphene only breaks with very specific angles. These are called petal structures. And we have now the tools to simulate this material. This is a simulation about 500,000 atoms. We try to mimic the experimental condition. We should see the elastic wave propagating. At the first, you still have the hexagonal topology, but as the elastic wave propagates, it becomes more like a spherical one. And if you shoot with enough kinetic energy, you break the structure. See again the elastic wave propagation, and now it starts to break. One advantage to be a theory guy, it's you can control time. So you can stop the structure if the simulation works. Oh, I don't know why not what, but it should show the fractal with the same, exactly the same experimental angles. We'll try one last time. We are shooting a nickel particle, mimicking the experimental condition, against a very large, this is a 500,000 atom simulation. See, you can see as the nickel particle impact the graphene, it starts to deform it, create the elastic waves, the elastic wave propagates until it breaks. See, the fractal starts here, here, and these angles is almost exactly the same experimental values. So this proves that we have very reliable theory tools to study these 2D materials. But the goals here, it's how to create. If you want real-world application, we need to create macro-scale structure, right? So the goal is to create 3D structure from 2D ones, or even better, if you could create 3D structure for one-dimensional ones. Well, one very simple way to do this is just mixing graphene oxide with boron nitride, freeze drying. If a theory guy like me can do that, it's a collaboration with giant groups in Rice. And you create these foams. And this, in general, graphene-based foams have two major problems. They are mechanically unstable. You just look at the structure, it breaks. You cannot hit them. Mixing this structure, you solve these two problems at the same time. The foams are mechanically very stable, and you can heat it up 1,000 degrees. Okay. The other way is change topology. You can go for graphene to the one just hold up. This is the scroll type properties. And many people think that the planar structure is the most stable one. It is not. This is the most stable graphene configuration. The price you pay for the elastic band, it's compensated by the gain in the Val structure. So if you have large enough structure, this scroll one is the most stable configuration. Or again, change topology. You can create, starting from this structure. In fact, this was proposed by a Chinese theory guy many years ago, and now it has been experimentally realized at Cornell by McKim groups. They use the electron beam to create the structure. So you can cut graphene any pattern that you want if you have the right machine. And now this is origami stuff. Origami stuff is just like origami, but you have cuts. So this is a very surprising result, again, using ballistic impact. This is just graphene. It breaks. If you shoot with the same kinetic energy for the same size, because you have this Kirigami topology, it can stop the ballot. So you have the same dimension, less mass, but it can stop the structure that the full structure. This is just because of the topology. Okay, but with now we have a menu of many different destructors, silicene, germanine, or a lot of destructors, but most of them are what's called van der Waals solids. It means that it's very convenient because it's very easy to exfoliate them, right? In general, they are stable because it's, or you can produce a CVD, or you can just take from nature. But if you go for the handbooks, you see that this van der Waals solid is a very tiny portion of the all possible 3D structure that you can cut. So the challenge would be, what about creating 2D structure for non-solid, for non-van der Waals solids? So this work was in collaboration with Giants Group in Rice. Cristiano was a postdoc at our group. Now it's a professor in the Federal University of Paraná. And the idea is very simple. And we start from 3D, very common material, hematite, you can find outside in the yard. And you use the liquid exfoliation. There is some, of course, there are some experimental tricks to do this, the amount of energy in the sonication, and also the kind of solvent you use. But just using this, we start from hematite and create what we call hematine. It's a 2D, very stable structure from hematite. It's very simple to do. You start from the hematite core, grind, and sonicate it for 50 hours with the right amount of DMF. So, and you produce what we call hematine. As it was a bold claim, we had a hard time with the reviewers, so we need to use a lot of experimental techniques to really prove that we have a 2D structure. So use a lot of X-ray, AFM. So you run analysis, you show the structure change from 3D to 2D, X-ray spectroscopy, and also to try to gain insight why this happens. We use the reactive molecular dynamics, the same kind I used in that simulation I showed before. And this is a revolution in simulation, because in general, force fields, you cannot break or create new bonds, right? But with this integration of reactive force fields, you can create and break bonds, but you do not take into account the electron in an explicit way. So instead of solving the Schrödinger equation, we are solving the usual Newton equation for molecular dynamics, but you can incorporate the chemical reaction. So you are doing chemistry without electrons. It's revolution. So we can handle, the record now, it's about 1 trillion atoms from the Chinese Academy of Science. So you are going almost in the real world in this kind of simulation, right? And the idea, it's a little complex. You have many parameters to optimize, about 100, depending on the system. And you can, the concept behind this is a very old chemical concept, bond order. If you remember your chemistry classes, in general, if you have, if you have a single bond, you have a bond order 1, double bond 2, triple bond 3, and in this way. That's a concept. So the force field allows you the structure to, in real time, to reorganize the hybridization, consider the environment. It's not you define as in the standard force field. And it's the interest, yeah.
So how do you actually make sure that you don't get something else? Like, if you would solve Schrödinger equation to find the new bonds, you could find something else in terms of hybridization or some other structure that would have, smaller energy.
The test, in general, use the heteroformation. It's a check. For carbon-based structures, it's not true for other structures, but for carbon-based structure, the error in the heteroformation is the same error about the experiments. We calibrate from DFT calculation if you have, but most of this data calibrated from the experiments from similar structures. So for carbon-based materials, quite reliable. Luis Felipe also used a lot of this code now. So the interest is increasing. See the number of papers using Reactive, it's exponentially growing. And now we have a new development in this field for a lot of class of materials. So it has become a very, very powerful tool to investigate structural properties and mechanical properties of nanostructures. Okay, so using we use the microscopy data to build the model as an initial configuration, optimize, and you see that this direction, it's the most stable one. It's surprisingly stable for considering that you are breaking a lot of bonds from the 3D structure and creating the 2D one. So we use the microscope data to generate the structure, to optimize the structures and compare again, simulate the spectra and see if they are consistent. Another unexpected result was a change from antiferro from hematite to ferro from hematite. A very strong magnetic signal, and you can see here, and it's stable. You can hit it, it's stable for at least room temperature. And to see it, our model was consistent with this. We run the usual DFT calculation using the CASTEP, that's a commercial code, GGA, plus Hubbard parameter, and use a very common functional. You use the Hubbard parameter optimized for a specific calculation from hematite. And you see that was, again, consistent. So that was a good consistency between the experiments and theory. The paper was published in Nature Technology last year. And for our surprise, this is a site that overviews scientific and industrial literature that was considered one of the most important papers of the year from the academia. Also because the catalysis increased of more than 100% going from hematite to hematine. There is some speculation that could be used for solar cells. This is a Brazilian magazine that it was not very precise, but it was okay for PR. And this year, this is from our Synchro National Facility also in Campinas. Another group repeat the experiment, use a different approach, and the data, also the experimental data and the theory data were consistent, so it's independent validation of the concept. As this approach is completely general, we decided to try for a more challenging structure for quasi-crystal. The quasi-crystal was invented by Daniel Schachmann, and there was a Nobel Prize in chemistry, and there was a hard sell in science to real prove that quasi-crystal could exist. In fact, there is a 2D quasi-crystal material, was an accidental discovery. This is a very beautiful picture of this work. And we tried to use the same approach. So we started from 3D quasi-crystal, exfoliated, and created the 2D, used the same recipe for experimental characterization, and we prove that, in fact, we have 2D structures, and you use the simulation again to see the origin of the stability. This is, you see the manganese atom enter the structure, expel the neighbors, and create some empty space. And we see the empty space in the microscope data, so it's, again, a very good agreement between theory and simulation. You see how it's very stable, surprisingly very stable. We are not using any substrate. So this is a self-supported structure. And we again use the same approach. Using the experimental data to create the initial configuration, optimize the configuration, simulate the spectra in compare to be. We are now trying another family, but the recipe, sorry for this. The recipe is the same, okay? And again, we run simulation, see, and also we explain why the catalysis increased 100%.
Why not reacts again?
No, this is, sorry, I forgot to mention,
No,
this
I-
is embedded atom.
Why?
Because the react force fields not very reliable yet for this class of material. So use more, it's it's easier to sell the paper if you use more acceptive force field than one it's under development. And also the consistency of the experimental data was very good. 6 months after these papers, also they also show that if you twist the graphene, you can also produce quartz crystal. Okay, so the general idea is we have a database of 5,000 structures now. So you cannot go in the lab for all this huge number. So use machine learning selection to choose the best candidate and go. I have 10 minutes. Okay. Oh, good. I didn't notice that. Okay. So, but all this fuzzy about 2D materials, I like to remind you that it's a lot of space to still use the old structure, one-dimensional structure, to create application of Mansell. I'll show here, it's 15 years of development on this project. This is in collaboration with Professor Ray Bergman in Dallas, in a 3 generation of my former students. They are now professors at Unicamp, Juiz de Fora. Leonardo is, in fact, professor here. It should be in the audience, perhaps. Okay, so we are now in the 4th generation of using carbon nanotubes to produce macro-scale functional application. The first one is the so-called buck papers. Use the same recipe of Chinese 2,000 years ago for creating papers, but we add nanotubes in the process. You can do at home if you have $5,000 to buy the nanotubes. Okay. So if you mix them, you produce this what's called buck papers. But for 20 years, nobody tried a very simple thing that was mix single-wall nanotubes with multi-wall nanotubes. When they did that, they found that there is a transition for non-auxetic materials to auxetic materials. That was an interesting result. If you don't remember what auxetic material is, auxetic material has negative Poisson ratio. It has this counterintuitive property. If you stretch along one direction, it expands along the course web. The physics of this system is very simple. You can build model with Lego at home, playing with this, and was a vindication of old molecular dynamic simulation. We proposed that would be possible to create auxetic material with pure carbons. Nobody believed at the time. It took almost 20 years to make the structure that's not the same, but which has the same topology. So this is the material, and it's like overcooked spaghetti. If you overcook spaghetti, you remember that you have stiffer parts when you have a bundle of them, but it's still flexible when you have the isolated structures. For simulate this, we cannot use in full approach, full even if you have the Chinese computer, the best computer in the world, so we have to combine molecular dynamic simulation for a small model and creating analytical ones to predict the structures. It took us 2 years to create this mechanical model, and this mechanical model is equivalent of the spaghetti. It was Victor work. It was very hard work, and this is, I consider, piece of art in terms of simulation. So we start from that structure, that's like a spaghetti, and produce this model, and this model reproduces inside the error bar the experimental data. So it's very amazing that you can create mechanical models that can mimic the mechanical property of very complex structure. The second generation of this structure was, instead of using the isolated carbon nanotube, you start from the forest. This is a real forest of carbon nanotube, grown in Dallas. You can extract this material, and if you twist them, you create the yarns. In the same way, you create silk. So you are reproducing the old Chinese technology for papers and for silk yarns. And depending on the way you do that, this is like you see the yarn being formed. if you twist them and put that inside paraffin, if you remember, paraffin has a huge thermal expansion, about 70, and physical ones tell you that if you have a twisted system and try to expand them, the only way to conserve energy momentum is rotating. So this is a very good artificial muscles. Every time is stronger than our own muscles and can stand it weighs 10,000 times its weight. I'll show you. So we can activate the artificial muscle, but by just use light. You see here, if I shoot light, the structure, it rotates. I can also make it rotate applying a voltage or heat them. In fact, the physics is all the same. It's the heating process, because what we do here, it's heating the structure, the paraffin expands, and it rotates, right? Okay. But the yarn information, the dynamic of the yarn information is still not fully understood, so I'll use the simulation to try to see how the yarn is formed. This is one of the advantages of theory again. I can put a camera inside the structure when it's been rotated. We cannot do the experiment without affecting the measurement, so you can do. And also we can see how they strain. This is a fully atomistic simulation. It's multi-million atoms. It looks like a continuum, but this is a fully atomistic simulation. We can see how the yarn is formed and the stress is being accumulated and dissipated. So again, the simulation tool is very helpful to optimize the process in the lab. The third generation, this is a very, you can create hundreds of applications with the same materials. The third generation was just, instead of create the yarn, wrap them using elastome. If you do this, it's spontaneously forming this very complex topology, like a crab. And when you measure the conductivity, we have a very surprising result. So you see, we are stretching the structure. We can twist and stretch, the conductivity doesn't change. You can bend, the conductivity doesn't change. You can curse the structure, the conductivity doesn't change. So if you remember physics, basic physics, it's difficult to explain, because that if you change the cross-section of the conductor, the conductivity should change. But here I'm changing the dimension of the structure and nothing happens. So again, this kind of simulation, we cannot use full atomic simulation. We can again combine simulation for a small structure and create the analytical model. And see, doesn't change. Next slide. Why it doesn't change? So this was a leader was also a postdoc here. Is now he decided to leave the university for more profitable oil job. He created this model with two phases. This is again a very, very nice theory work, and the structure showed that if people from statistical mechanics here, perhaps not. This is not really a super percolative state, but it looks like. The explanation in the end is very simple. Because you have this yarn, and this yarn contains millions of structures, even when we stretch them, the contact between the nanotubes is never lost. So even when you stretch, then you change this, but it still remains a path that the nanotubes are connected. As the current flows, where the resistivity it's easier, so you can explain why this happened. Again, when you compare with the experimental data, the agreement between the simulation and the experiment is remarkable well for a complex structure. Okay, this paper was considered one of the 100 best papers of the year. Again, good PR for the funding agencies. And okay, we have the fourth generation. The fifth generation, we use the same approach, but instead of use the yarn, we decide to test with polymers. So we use polyethylene and also phase change metallic alloys, and you produce the same kind of results. The paper we appear in Science next Friday. So thank you very much. I hope I have demonstrated that you have a lot of very reliable tools to study mechanical and structural property of low-dimensional material. Thank you very much for your attention.
Questions?
I have a question about the hematite, 2D hematite.